something known as quantum confinement. Yeah. Okay. So something known as quantum confinement. Okay. So when we go to these smaller structures, so these the motion. So mostly what we are interested in, let's say any of the properties, electrical or mechanical or let's say optical, magnetic properties. Most of the properties are due to the how the electronic structure is. Okay, or the basic is how the electrons are arranged in this in the energy levels in the orbitals, or how do you feel the electrons in the material. That means, so when we talk about atoms, for example, and so you can solve a hydrogen, a hydrogen atom, so you can solve it and you can know, or that electron has discrete energy levels. So similar things actually happens in nanostructures, and that is what we call it as a quantum confinement, because when we are talking about the electrons, basically uh, they can behave as particle as well as wave, right? So they have a dual nature, and typically, like you describe the wave nature by its wavelength, defined by the de Broglie wavelength. But most interesting thing is, then how do you define or describe its motion or its electronic structure of a quantum mechanical particle? So this is like a very basics of quantum mechanics. For example, if you want to know its position, its momentum, or energy eigenstate, and so on. So that is actually given by uh, sorry. Uh, so that is given by let me see, this by the Schrodinger equation, right? Change the color. Me. So that is normally defined by this or described by Schrodinger equation, which is very similar to like you have Newton's laws of motion for classical particles. For quantum particles, we have the Schrodinger equation which define the behavior of the particle. Then how do we write down the Schrodinger equation? So if I want to write the time dependent form, so anyone can tell? Yeah, I mean, the physics guys should tell how do I write a time dependent Schrodinger equation?
Sir, H psi of RT equals to E of psi of
Slow,
RT.
slow. Yeah, come
Sir,
again.
H of psi of RT equals to E of
Yeah,
energy of E of psi of RT.
okay. So E of psi of RT. Okay. So this is like in a three-dimensional form. So I'm writing it R as a position vector and T is time. And what is H?
Is the Hamiltonian.
Yeah. So how do I write down the Hamiltonian? Like,
Kinetic energy plus potential energy minus
okay. So it is, sorry. So kinetic energy plus potential energy. So then how do I write down here the Hamiltonian? So normally we write it down in a operator form, right?
So del square psi plus v psi.
Sorry, del square psi, and there is nothing else,
Plus v psi.
plus v. Okay, psi rt will be equal to e psi rt. Is it correct?
I think, sir,
You
minus h squared by 2f great square psi of RT.
right. So there is something minus h cross square by 2m del square psi rt plus this is the potential. So this is your kinetic energy part. Okay, and this is your potential energy part, and then this is what defines your energy eigen function or eigenvalues. And this psi, this wave function is normally is a complex wave function. So in quantum mechanics, this wave function is always may not be a real wave function, so it can be a complex wave function. Okay, and when you, so basically to understand describe a quantum mechanical behavior of a particle, so what you need is first define the Hamiltonian, right? So you have to write down the Hamiltonian, which is nothing but it's you have to write down the kinetic energy term and the potential energy terms that is experienced by the particle or your quantum mechanical particle, and then you have a wave function psi, okay, which defines it's like it's a function of position and as well as time. And then if you solve that, so it is basically like a differential equation. So if you solve that, so you obtain what are the different energy eigenstates the particle, this quantum mechanical particle possibly can in which state it can stay, okay, or occupy. uh, and mostly this wave function is a complex wave function. Then what is actually a real is basically what we know as a probability distribution, okay, and that we find out normally by calculating the psi star psi. Okay, so this is your probability of finding a particle at certain position r at a in a at a particular time t. Okay, uh, but again you can also calculate energies, momentum, and other parameters for the quantum mechanical particle. But let's not, without going into the details of that, so let's say we have, so one version is this time dependent version, so we have psi as a function of time t. Now we can also write it down. So in fact, this E, what we write here is not actually the time dependent form. Okay, so you said it is a time dependent form, but actually you normally don't write E psi as a time dependent form. So what you write is I h cross del psi by del t. Okay, so this is your time dependent Schrodinger equation normally. So you don't write E directly like it is. Okay. So rather you write it like I h cross del by del t, and then you have a version where you can write it down in a time independent form. Okay, so that means you can separate the position and the time dependence. And how do I write that? So that I write down like we did it before. Del square psi rt plus v psi rt will be equal to e of psi rt. Okay, so this is, you can write it down in a time independent form. So that means here instead of psi rt, so I should not write psi rt anymore. Sorry. So instead, what I would write, so I have only the function as a function of r. Okay, so the function of t is does not exist anymore. Okay, so this is how the time independent form would look like. Again, the psi here, this wave function that describes the quantum mechanical particle, is still a complex wave function. Okay, and all these parameters here are time uh, independent form. Okay, so that means if we want to describe a quantum mechanical particle, for example, in this case, what we are really interested in is electrons, right? So electron is a quantum mechanical particle, and what we need is to write down the Schrodinger equation. We need to define the Hamiltonian. Okay, so define it Hamiltonian, and then you need, like, if you write down. Okay, so before we go here, so how do I write it down in a one dimension? So in one dimension, this differential equation will be quite simple. So d square psi by dx square plus v into psi. So here, since it is one dimension, so I can write it down as a function of x, let's say. So psi of x, and of course, if the potential v is 0, in that case it becomes like a free particle, right? So it's a free particle, and which will have energy of h cross square k square by 2m. Okay, so k is basically your wave vector, which is defined by your de Broglie, will be related to your de Broglie wavelength lambda. So that means when in quantum mechanics, for that matter, for any quantum mechanical problem, so if you know what is the Hamiltonian, so you have to define it properly, and if you know the wave function, so you can find out this energy eigen functions or eigenvalues, sorry, so energy eigenvalues, so which basically will describe which energy states the electron is going to occupy uh, in that, or what are the possible energy eigenstates that is available for the electrons. Okay, yeah, so this here I just mentioned, or the text what I just told you, like how one can solve a typical, like a Schrodinger's equation to find the energy eigenstates. And one of the most basic problem you might have solved quite a number of time is, let's say if I put a particle or an electron in a box in a one dimension, let's say. So one of the simplest problems in quantum mechanics, So now let's say the particle is confined. So it is confined here in this box. This is a one-dimensional box with a length a. Okay, so that means, but it is still a free particle within the box. So that means the potential energy within the box is zero, and the potential outside the box is infinite. So when you go below, when x is less than 0, the potential is infinite. Between 0 and a, it is 0. And so you can write it down in a, let's say, v is 0 when x is between 0 and a, otherwise it is infinite. Okay, so this is one of the very simple problem in quantum mechanics. And then the problem is how, what are the possible energy states we have to find out. So then how do I write down the Hamiltonian in this case if I want to write the solution? So here, so anyone can tell what will be the, in the operator form,
So
let's say. So
minus h cut square by 2m d2 psi by dx2 plus
yeah,
0.
d square by dx square psi. Potential is anyway, v is, so of course you have to make sure, the potential is zero within the box. And the since the particle is within the box, so we are not worried about what is happening outside the box basically. uh, so within the box the potential is zero, so which will be equal to e. So your H psi will be equal to, you can write it down in this form. So this is your basically the Schrodinger equation. And once you write the Schrodinger equation, so to solve it, so you need some boundary conditions, right? So what is the boundary condition here?
At x equals to 0 and x equals to a, the wave function will be 0.
Right. When x is equal to 0 and x is equal to a, psi, this is a one dimension, so psi x will be 0. That is clear because the particle will not exist or cannot go outside the box, so it is bounded inside this box. So therefore the wave function has to be 0 at the boundaries, x equal to 0 and equal to a. Then what will be the solution of this equation? This is our Schrodinger equation. So we can take a trial solution, right? We can try, so how do I write it? So this is square root of that plus b. I can write down the same cosine function of x. So this is a possible solution of that particle. And then if you apply a boundary condition, boundary condition tells you that b will be equal to 0. Okay, so if you substitute this boundary condition at x is equal to 0, so if you substitute that, so you know what is psi, and you can substitute in this equation, and then you know what will be the value at x equal to 0. Psi will be equal to 0, so that boundary condition leads you to the uh, uh, tells you that b will be equal to 0. So that means actually the wave function will be like a sine function. Okay, and this is your wave function for the particle. Then what are the energy states? So how do I find that? So how do I find the energy eigenvalues?
Putting this back into the equation.
Okay, so if I substitute this psi in this equation, okay, so this is my wave function, and if I substitute that, so what I will get? So this is the wave function. Okay, yeah, what is next? So you can calculate. Okay, so I am not going to do it the step everything because you already know it. So d psi, so you calculate d square psi by dx square and substitute that, and then you will get your energy eigenvalues as n square h square by 8m a square. Is it correct or not? Or if I write it down in terms of h square, so it will be n square h square by 2m a square. Is it correct or not?
Yes, sir.
Yes?
In the second term, it's
No,
There
pi
is a
square term.
pi,
pi
Sorry?
square.
Pi square also.
n square is with pi square.
Pi square missing, sir.
Yeah, pi. Here we will have pi square. That is true. So you'll have a pi square term. So h cross, yeah, h got, yeah, right. So what is n? So n can have values like 1, 2, 3, and so on, right? Can we have n equal to 0?
No,
No,
sir.
sir.
No, sir.
Yeah. Why not?
Because the wave function will be vanished if we put n equals to 0.
Yeah, right. So if we put n is equal to 0, so that means energy is basically 0. So that means the wave function will vanish, and which cannot happen because we know the particle is inside the box. So you can also calculate. So here in this schematic, this figure, so this is all these things have been summarized. So we have the energy. These are the different energy levels, so which is discrete in nature, so corresponding to n equal to 1, 2, 3, and so on. And this is the wave function, uh, and this energy eigenstates, the different energy eigenstates, you can call uh, in context of electron, you can call it as its orbital. Okay, so of course what we have is like a one-dimensional picture, but it is something like similar to this orbitals what you have in for electrons when it is bound to one atom. Okay, and this is the wave function, and this is the probability distribution, how it looks like for different energy eigenstates. So one thing what we already see here, where interesting thing is this energy depends on inversely proportional to a square. Okay, so that means smaller the dimension or thinner it is, or if I decrease the size, let's say, the energy is going to this is going to increase. So normally also this is if you calculate the energy difference as well. So this is also will be proportional to 1 by a square. Okay, so that means the energy difference between the ground state and the excited state. So these are like our, so this n equal to 1, n equal to 2, n equal to 3. So n equal to 1 is your ground state, and then n equal to 2, 3 are your excited states. Now if I want to fill the electrons here, for example, uh, so I have to follow the Pauli's exclusion principle, right? So that means I can have two electrons here in the ground state, and then I keep on filling up the electrons in the next available energy. So if I have, let's say, 6 or 5 electrons, so I first put 2 electrons in the ground state, and then I have 2 more in the first excited state, and then I put 1 more in the next n equal to 3, the second excited state. And that is how you can fill it up different energy levels. And this is what we do with electrons. So electrons are basically following the Pauli's exclusion principle. So this represents a spin up and spin down electron, right? So one is a spin up electron and spin down electron, and this is how I can fill up depending on how many electrons I have. And normally this is your highest energy level, and this is normally you can also call it as a Fermi level. Okay, so you might have, most of you already know about this Fermi level, that is like below the Fermi level, all the electrons energy states are filled. So in electrons, they occupy all the energy levels that is available up to the Fermi level. So you can in fact also define the Fermi level or Fermi energy as well. So in all these calculations, we have, like, when we are calculating these energy eigenstates, so we actually are not bothered about not much of temperature. Okay, so we say, okay, everything we are at 0 Kelvin. Then how do we understand the electrons distribution as a function of temperature? So that comes from your well-known distribution, Fermi-Dirac distribution function. Okay, so this temperature changes. So basically, what this temperature is going to do is, right? So we have these energy labels. It is not going to change anything in terms of the energy level as such. Only it changes the distribution or how the electrons will be distributed in these energy levels, right? So it is not going to change anything. These orbitals or the energy states or the energy levels remain the same. So there is no change. Only how the electrons are filled, they will change. And that is typically described by this Fermi-Dirac distribution, which is, I already wrote it down here. So this is again a statistical distribution. So a classical particle will always follow a Maxwell-Boltzmann distribution, but a quantum particle can, so depending on whether it is a fermion or a boson, so it can follow different distribution. And typically electrons being fermions, So they follow this Fermi-Dirac distribution, which is so what is here mu? Mu is your chemical potential. Okay, so which will be equal to the Fermi energy at T equal to 0 Kelvin. But for most of the metals, in fact, this chemical potential is almost always very close to the Fermi energy, so not much different. But of course, this mu, the value of mu depends on temperature, so it will change as a function of temperature. So if I want to plot this function as a function of, so this is my distribution as a function of energy. So at t equal to 0, I have, so this is EF. So that means, so when you look at the function, so for energy E less than EF, all the levels are occupied. Okay, so the distribution is as such, all the levels are filled, and therefore this distribution is 1. Okay, and then at E equal to EF, so all the energy levels will be empty above E. When E is less greater than EF, all energy levels are empty. So that means there are no electrons there. So all the electrons are only present below your Fermi energy, and that's why your distribution is Fe will be 1 below EF. But as you increase the temperatures, and this is will be T equal to 0. But now if you increase the temperature, so there is some electrons can jump to a higher energy levels, because they will get this energy kBT, okay, and then they can jump to higher energy levels, and the distribution will change accordingly. And then as you keep on increasing the temperature, you go to higher temperature, so like you will have more and more electrons you will find above the Fermi level, because they will have this energy kBT, which will uh, this thermal energy basically, and they can go to higher energy levels or above the Fermi level. So this is how the distribution would be of the electrons as a function of temperature. But when we say the electrons energy states, they are always there, whether they are occupied or not. So the occupancy depends on the temperature and governed by this Fermi-Dirac distribution. But these energy levels, all these energy levels are always present. Okay, so I mean all these are different, let's say, energy states that is possible for the electron, and these energy states are always are there. So only thing whether they are occupied or they are empty, so that is defined by the temperature. Okay, so this is kind of yeah, we are yeah, kind of close to the end. Uh, but what is interesting, or what when we look at materials, this is not like we don't have a discrete energy levels, right? So it is not like, and we do not talk about only one electron, but there are like many electrons. So can be uh, like Avogadro's number, like that kind of electrons you can have in a solid, and and that makes the solids, the behavior very interesting. Okay, and so this quantum mechanical problem which we solved for a 1D case is a very simple way to understand how the electrons the energy states they can form and how they fill up. But in real case, a real picture in real solids, this picture can be very different. Although not easy to solve, but nevertheless you can start with your Schrodinger equation here again. Like we have, this is a three-dimensional form again. Okay, so this is your, so we can say, let's say the particle is now is confined in a cube, right? So it is confined in a cube, so of length a, right? And so you can write down the Schrodinger equation like this, and just if we say there is no potential outside and the potential is zero, it's again a free particle. So we can write down the energy eigenfunction as, so there we had n square. Instead of that, we can write it down as nx square plus ny square plus nz square. So if we have a three-dimensional quantization, okay. So this quantization happens now in three dimension in all three x, y, and z, and the energy eigenvalues we can write it down like this. And what will be the wave function? So if the wave function before, so how do I write down the wave function? Anyone? So how did we write it for a one-dimensional case?
Sir, nx by x by a into sine nx by y by a
Mm-hmm. Yeah. So we
into
can,
sine n
yeah,
y pi by a.
right. So we have basically, we can write it down something like this. This is in three dimension, a particle in a 3D box. Okay. So we will continue with the discussion of this in the next class. So we'll continue with the review thing tomorrow. Okay. If you have any question, anyone?
Hello.
Yeah.
Yes, sir. In the Fermi Dirac distribution, in this figures,
Mm.
please.
Mm.
For t is equals to 0, we
Yeah.
get a Fermi level. But for the t greater than 0, how
Mm.
can we define the Fermi level?
How can you define the Fermi level? The
We
Fermi
know,
level is defined already at t equal to 0. So normally for a solid, you don't like if you have t equal to, I mean, let's say, so the Fermi level is like a, what do you say? It's a uh, mathematical concept. Okay, so there is not like I mean, in by mathematical definition, what we say is Fermi level is the energy level up to which the electrons are filled. Okay, so that is the Fermi level at t equal to 0. But as you see here, the electrons are also occupying energy levels above, like when you have at a finite temperature. So electrons can occupy energy levels which are higher than the Fermi level. So there is no, so normally you don't define a Fermi level, rather that's why we have this chemical potential. Okay, so this is what the chemical potential will define basically what is uh, the electrons energy level. So normally the Fermi energy is as t equal to 0. That is what you define. Or is it clear or not?
Yes, sir.
Or what do you want to know? I mean, Fermi level above at a finite temperature is, yeah, you can write an expression for that. like as a function of like in terms of the temperature, you can write it down, but normally it is not. I mean, you define. Okay, for a metallic case, it is quite simple. Okay, uh, and typically the Fermi level will be always very close to the value at T equal to 0. I mean, unless you go to like above the melting temperature or like that. Okay, so most of the at working temperature, your Fermi level will be very close to, or so the difference very small from a T equal to 0 value. But in case of semiconductor, it can be like, it depends on the doping and so on. This Fermi level can change. Okay.
Okay, sir.
Yeah. Anything else? So tomorrow we will also continue with this basics. So basically, like describing the density of states. I mean, most of the things what you already have done, most of you. And if those who, anyway, I will share this uh, today. I will put it in the Google Classroom because I have already made it. So, I mean, you can see what we are going to discuss in the next tomorrow's lecture as well. Okay. And yeah, anything else? Any other question? Yeah, just let me know if you have any like the students. So I'm not sure if. Let me, okay, so let me stop. Yeah. So others like if you are not familiar with this concept, so there are books which is like basic quantum mechanics, or I mean online you can also find it. So lots of materials available, basic solid state physics. These are all available quite easily. And if you have any question after going through the material, let me know.
Hello, sir.
Yeah.
Sir, whatever was taught in this class, is it a prerequisite for this course? Because I'm from manufacturing domain and I'm not actually familiar with these topics.
Yes, actually, I mean, these are will be helpful because like in this course, so we are going to discuss a lot about, let's say, electron transport, for example. So for that, you need to know something about the band structure, the the energy gap, how it arises, okay, and also like the for transport properties, like if you want to study the electrons transport, okay, so semiconducting properties of the material. So these things are actually a little bit you require those things. I mean, we will not use it exclusively for most of the topics, but this will give you a better understanding of the nanoscale phenomenon, or different nanoscale phenomenon that is happening in different materials, because we will discuss about metallic systems. We'll also discuss about uh, semiconductor nanoparticles. Okay. I mean, most of the applications, if you see, like solar cells, energy storage, I mean, many of them are what we exploit is their semiconducting properties or electronic properties, basically. Hmm. So therefore, a little bit of understanding of that will be helpful. I mean, it is not that difficult. I don't know if you have you done any course on quantum mechanics or solid state physics or condensed matter physics?
No, sir. No, sir.
Okay. Yeah. So then, yeah, just go through that if you are comfortable. Yeah, you can decide. So I cannot. I mean, definitely some of these concepts we will use, uh, because I mean I may not explicitly mention that during the class. So what could happen is like I just say, okay, yeah, you know, the semiconductor behaves like this, or the it's a the energy level will be like this, or the energy of a free particle will be like this. You know, like h cross square k square by 2m. So these things will help. I mean, if you understand it or know about it. Hmm?
Yes, sir. Thank you, sir. Thank you.
Yeah. Okay. Okay. So if not any other question, so we will stop and then we'll see you tomorrow. Okay. Thank you.